Uh, well, everybody, welcome to this afternoon's version of Math Club. It is my pleasure to introduce to you VanLandingham, who is going to tell us about current topics in lattice-based cryptography and maybe get some more think in some ongoing research. So, without any further ado, Julia.
Yes. So, because it's totally a shameless plug for a project, I will tell you a little bit about myself. I'm a fifth-year PhD student here studying this stuff, and I work with Dr. Daniel Martin. We'll be teaching a discrete math course next semester, so some of you guys might have. But before I can tell you anything about the project or what I actually do, I should probably tell you what cryptography. I might cover. Okay. Wait, am I not working off?
I think the down arrow maybe works.
Okay, fixed it. I should tell you what cryptography is before we do anything, for those of you who aren't familiar. In cryptography is something that's currently happening. Okay, it's a way of protecting information, much like clicking things. And so this actually dates back to like 2000 BC in ancient Egypt, where they actually used hieroglyphics to kind of conceal things from other people groups. So like they would conceal their pottery recipes, for instance. Different groups of people had different kinds of hieroglyphics that they would use that only was known to them. Moving way into kind of modern times, Julius Caesar invented what was called the Caesar cipher, and he actually did this because he was paranoid about his advisors, which at that time seems crazy, but obviously we know that was like pretty reasonable. And so that's what we know as the first modern cipher. Of course, it's super broken now, but it started off on a long path. About 50, more than 50 years ago, but not that much more, there was the Enigma machine. So this was one of the most famous systems of cryptography of all time because it was thought to be the unbreakable crypto system, which of course then the Allies broke, which was a major part of winning World War II. And so this is actually a photo that I took at the National Cryptologic Museum. This is an Enigma machine. And this is actually one of 13 machines that was specifically made for Hitler and his posse. And you really can't see it in the photo, but there are like little numbers and letters down here, and they're red on this one, which is how we know that this is one of those 13, specifically for Hitler. So in this machine, part of what needed to be done before any communication could happen was these plugs at the bottom had to be placed in different locations. And based on where those plugs were, different things would happen. And so two people would need to have the same plug locations first, and then they could communicate. And then basically this is like a normal like QWERTY keyboard, except when you pressed one button, there would be a light that would shine a different letter. So maybe I press E and a light shines that's W. So E turns into a W. And you type out your word and then you have your message. And whoever had the same configuration could then just do the reverse. So why should you care about cryptography? Well, it's awesome and cool, and I'm telling you about it. But in the broader scheme of things, you are Bob. You like buying things from Alice, the Amazon server, right? I just bought things today from Alice. And I have to give her my credit card information, which I probably don't want Evil Eve to have, because Evil Eve is going to spend all my money. So what cryptography lets us do is put a little lock on this communication so we can encrypt that credit card information. Now Bob's happy. Evil Eve is sad. That's fine. She's evil. She'd be sad. So that's why you should care. Now I told you that this dated way back to like the 2000 BC era. But in kind of more modern times, we basically have two classes of systems that are used. even back to 2000 BC. So since then, up until rather recently, we've used what are called symmetric or private key systems. So in this kind of system, Alice and Bob, the two parties in the communication, are going to agree on some secret piece of information that they're going to call a key, S. And they're going to agree on some standard algorithm. So thinking back to the Enigma machine, the algorithm itself was baked into the machine. And she had to both have a physical machine. And the secret information was where those plugs should be at the start. Once you agree on those things, then Bob can use all that information to encrypt his message. It's secure, so when he sends it to Alice, anyone looking on can't get any information from this encrypted message. So they don't have that secret key. But Alice does. And so she can just undo each operation of the algorithm and get the message back. So we do a really quick example, is a one-time pad. So if I have a message that's in binary, so just zeros and ones, I'm also going to have a key that's in binary. What I can do is do what's called an exclusive OR operation. If you're familiar with quadratic arithmetic, it's the same as taking addition 1, 2. So basically just all of the entries we're going to add, just like normal, except a 1 and a 1 together make it 0. So when we do that, now at the bottom we have ciphertext. Each one of those digits, we don't know what it came from. A 0 could have come from 2 zeros, or it could have come from 2 1s. So we can't recover any information without having the key ourselves. So this is awesome, this is great. It's perfectly secure, you can get 0 information from this. However, it's completely impractical because as soon as I use that key a second time, then now someone who's looking on, if they have both ciphertexts, can get a little bit of information. And so if I use that key multiple times over, I'm leaking a little bit of information each time, and eventually an evil Eve can totally recover the key, and that means all my messages are no longer secure. So in order for this to actually be usable, I would need to generate a new key every single time. And why don't we like that? Well, we have to somehow get this key to each other, Alice and Bob, before any communication can happen. And that's really annoying. That's kind of a really big deal, right? So in the Enigma machine days, they would have a physical code book of like written down, this is where the plugs go on this day at this time and all this. And they would have to physically exchange these books. Then they can send messages. So this is not fun. Don't like this, but this is how everything has worked for about 4,000 years. So right now, in today's world, obviously we don't use one-time pad. We use more sophisticated algorithms like the advanced encryption standard or the data encryption standard. This one's actually been kind of phased out in the past 10, 15 years, but AES is like very standard right now. We're not going to talk about those because they're annoying. You have to exchange these keys ahead of time. So in order to combat this, in 1974, Ralph Merkle proposed the first public key system. And I want to pause for a second. That's not that long ago, right? That's about, 51 years ago. But I told you cryptography has been around for 4,000 years. So this is shockingly new stuff, and yet this is what we do every single day. This is how all of the cryptography works right now, is we're doing this. So this is really big. He proposed this system, and what's going to happen is Alice is going to tell the entire world some public information. Bob is going to also say some completely public information, and somehow magically, well, mathematically, they're going to have a shared secret piece of information. So you can almost think about it like an inside joke, where like I say something, you say something, haha, we both get the joke. Except Alice and Bob have never ever met each other. So there's no setup of the inside joke. So how is this actually going to work, basically, is Alice is going to say, hey world, I know how to solve this really difficult math problem. Bob is going to send a message as the solution to that kind of math problem. And then Well, Bob has a solution because he made it, and Alice can get the solution because she can solve math problem. And we'll do an example of this. This idea was so ridiculous to everyone that no one really liked it. They were all dismissed it, and it didn't get published for 4 years, including his advisor didn't believe in him or this idea. Most commonly, the math problems that Alice is going to say she can solve is factoring and discrete log problems. So if you think about factoring, it's really easy to take two numbers and multiply them together, even if they're really huge. It's just like pretty simple. We just do it with a computer. But it's very difficult to factor that back out, right? If I give you a number and I tell you that it's two factors, they're both 100-digit long numbers, you're going to not be able to factor that back out. But if I already know one of the factors, well, then I'm cheating. Of course, I can solve this hard math problem. And that's what Alice is doing. So Alice, before anything happens, is going to create an instance of some hard math problem, and she's going to be able to solve it because she's cheating. She has some secret information that lets her solve it. So she tells the world the problem and not the solution. And then Bob can use that and encode his message as a solution. Well, it's hard for everyone else to solve, so when he sends it back, it's totally secure. But remember, Alice had a secret piece of information that lets her solve it. So this is great. Almost. There is impending doom upon us. Some of you might have heard about this. So all of these algorithms are secure because the math problem behind them is hard to solve, right? If everyone could solve the hard math problem, well, then anyone could just take that encrypted message and solve it and find Bob's message. So it's really important that it's hard for everyone, but Alice has a cheating method. Well, in 1994, Peter Shor published an algorithm that would show that we can solve most of those hard math problems that we're using if we have a quantum computer that's large enough, which we don't, so don't worry. But it is something we should think about, right? So in 2017, NIST, the National Institute for Standards and Technology, said, hey, this is enough of a threat that we should start thinking about this. We need some new crypto systems that are going to be secure when a quantum computer does come about. And of these, there are 4 that have been standardized, and 3, sorry, I think that should be 4. The 3 of them are based off what we're going to talk about today. And actually some major companies, including Google, Amazon, and Apple, have already started implementing these new algorithms, even though we don't have quantum computers that are really a threat quite yet. So what does this actually mean? Well, this means that most of the common protocols we use right now are not secure. And as recently as May of 2024, there was actually a lot of records broken by Chow et al. Quantum factoring a 22-bit integer. Previous record, I believe, was 21. Not 21 bits, the number 21. So this was like leaps and bounds better, which caused more concern. The good news is that all of those private systems I told you about are totally fine. We might have to adjust a little bit, but they're good. The bad news is that we use the public keys to transmit the private key information for those systems. Because we have to exchange that before we can communicate. So we need new algorithms, right? That's the crux of the matter. And we need these new algorithms to be based off different kinds of hard math problems. They need to be hard math problems that are difficult to solve by a classical computer and by a quantum computer. And there are basically 4 classes of problems that we typically use. There are lattice problems, which are by and far the most popular, and that's what we'll talk about for the remainder of today. There are multivariable calculus problems, coding theory problems, and what are called elliptic curve problems, which if you're not familiar with that, you can kind of think about it like a super high dimensional geometry problem. That's kind of lying, but just like, it's fine, we're not talking about it today. So we're gonna talk about lattices for the rest of the day. So I should tell you what it is. It sounds super fancy. Genuinely, it's just a grid. This is a lattice. It's a grid with a few properties. So we're always going to have a 0 point in the lattice. And we're going to get this by taking different combinations of what we're going to call generating vectors or basis vectors. So basically, if I take blue and red, I can add them together in any different way, and I'll get any of the other dots on my plane. So I could do this combination, b1 plus b2, and that's how I get this new purple vector, or 2b1 plus b2, and I get that purple vector. Very, very importantly, we're only going to allow integer combinations of these b1 and b2 vectors, which is why we have these discrete dots in a grid, and we don't have the complete plane who's not a true vector space. So more formally, a lattice is made up of all integer combinations of a set of basis vectors of Rn. For today, we're probably just going to assume that these basis vectors are mostly integers, but they do not have to be. So in this lattice world, we need to have some hard problems. And the first of these is called the shortest vector problem. So if I give you a set of vectors, that's my generating set for the lattice, I want you to tell me what the shortest non-zero vector is in the lattice that they generate. Go. This generates a lattice. What's the shortest vector? Can anyone tell me? Yeah.
-A.
Maybe. That's a very good option. It might be just like red minus blue. And that could be one of the shortest vectors, but how would you know? Maybe there's some other crazy combination that's actually shorter. And the answer is there's not really any way, because we don't see it. But as soon as I give you the whole lattice, well, then we can see it's actually green. And so actually, if you did b minus a, you would get this vector here, which is short, but it's not the shortest. So it's very difficult, just given those basis vectors, to actually find a short vector in this lattice. Now, of course, 2 dimensions, it's not that hard, but we're going to be working in like hundreds. So often we only care about actually finding a vector that's short enough. And that's going to be based on what the problem is, what enough means. So sometimes this purple vector is going to be good enough. And this problem is actually an NP-hard problem under what we call a randomized reduction hypothesis, which basically all you need to know is it's among the class of hardest problems that we work with. The other kind of problem we work with lattices is called the closest vector problem. It's very similar, but now I'm going to give you that same set of vectors, so a basis, and I'm going to give you a vector that's not in the lattice. And I want you to tell me what the vector in the lattice is that's closest to that guy. So I'm going to give you this lattice, blue and red, they generate some grid. I'm going to tell you green square is not in the lattice, but it's close. And we don't really have any good way of telling what the closest vector point or the lattice point would be. Maybe it's red vector, maybe that's the closest. Or maybe there's some other weird combination. It's very difficult to tell. But as soon as I show you the grid, well, then we can immediately see that this green dot is closest. Just like the shortest vector problem, often we only care about finding something that's close enough. So maybe purple is good enough. This problem is actually a true NP-hard problem with no randomized reduction hypothesis. So this is at least as hard as the shortest vector. All right. So we're going to go through an example of what this would actually look like in practice. These are the hard problems that our crypto systems are based off of. What happened? Well, let's look at what an evil Eve might be able to figure out from a crypto system based off this lattice. So we're gonna have this basis vector here of red and blue. These are our basis vectors for some lattice. This is Amazon's public key information. So she's gonna publish this to the entire world. So any Bob will have it, obviously Amazon has it, but also Eve has access to this. Now, Bob behind the scenes is secretly going to encode this point as credit card information. He's not gonna reveal that to everyone. What he will reveal is a little bumped version of this. Right, so if we have just the dot, well, finding a linear combination of red and blue is equal green circle, that's actually very easy, that's just linear. But as soon as we do this little bump, it's gonna become quite difficult. And so this is actually a closest vector work, right? I want to find either just the green dot square information, I want to find green circle. So I have green square, Amazon's public key, I want to find green circle. So let's see how well Eve can do. Let's look at what the most kind of simple thing possible would be. And this is a method called the Bayes nearest plane algorithm. So Eve has this information, public basis for the lattice and the encrypted credit card information. And what she wants is some linear combination of those basis vectors approximately equal to the target vector. Well, we can see that this is actually just a system of two equations, or if we know linear algebra, this is something we can very easily solve. And so we can just solve this to find A is about negative 6.6, B is about 10.4. But lattices are only allowed to have integer combinations of basis vectors. So what's the simplest thing we could do to make this a lattice point? We can't have 0.6 and we can't have 0.4. Let's just round them, right? If you need integers, let's just round them to integers. And if we do that, Eve is going to find this to be the guess for Bob's credit card information, the closest lattice point. All right, so pretend that we don't know anything about Bob's real credit card information, right? We're Eve right now. This is the information Eve had, and this is her guess at what Bob's credit card is. Now, we don't know what the whole lattice looks like. We secretly do know that this is wrong, but maybe it's like close. It's not at all, it's pretty bad, which is really good for Bob, right? Because we don't, Bob doesn't want Eve to steal his credit card. So what went wrong here though? Like we did a lot of things that made sense, right? We solved the system of equations, we rounded some, we didn't do anything crazy. Well, while we didn't round anything crazy, we only rounded by a little bit, the vectors that those coefficients are attached to are quite long, right? They were long, and they also kind of went in the same direction. They weren't orthogonal at all. So when we did this little bit of rounding, it actually bumped our answer by a ton. And so that's why Eve got such a terrible approximation, a terrible guess. It's good for Bob. But if we look back here, this is the lattice. Can anyone see a different set of vectors that would serve as a basis? So another set of vectors that would be nicer, just in general, that's simpler to generate all the dots. I see, yes. This one right here, and this one, if we took those, we could still get all the dots, right? By doing integer combinations. And those are just way nicer. Right? Why would we use these ugly, long ones if we could use simple ones? And that's actually exactly what Amazon's private key is. So this is the secret piece of information that Amazon keeps held back that's going to allow her to recover Bob's credit card information, even though Eve couldn't. So let's see what that looks like. So this is what Alice has access to, this private key information and the same encrypted credit card. So again, we're going to use a private basis, and we're going to try to find this linear combination to equal approximately that target vector. Well, we can already see this is going to be a way simpler system of equations because there's a lot of zeros, right? We're just going to have 4a equals 3.1. We can probably do that just about in your head. And 3b is equal to 14. So when we solve that, we're going to get a is about 0.93, b is about 4.7, and it makes sense still to just round. And so Alice's guess for what that closest vector point for Bob's credit card information is 15.4. So this is what Alice had access to, and this is her guess for what Bob's credit card information was, which if you remember way back, this is actually correct. So again, what was the difference? Because the process we did here was exactly the same for Alice and Eve had a terrible guess. Alice got it completely correct. Again, the difference is in these red and blue vectors. These ones are perfectly perpendicular, and they're also shorter. And so when we do this little bit of rounding, it doesn't bump our final answer nearly as much. So in general, we like vectors to be shorter and more orthogonal. Most of the time, we're not going to be lucky enough to have perfectly perpendicular, but the closer the better. And we actually do have ways of taking really bad bases and turning them into good bases. So for instance, like taking a public key and turning it into a form of a private key. And these are called like LLL, Lenstra, and Roche, Lock, Horkheim, Zoltarov, and Hermite, Horkheim, Zoltarov, which I'm never going to say again. We're just going to say LLL, BKZ, HKB. That should make you really worried. Because I just told you the entire point of this is that Eve got a really bad guess because it was a bad basis. So if there's a way to turn bad bases to good bases, that's super concerning, except it's actually not. Oh, they also give a nearly short vector. So not only are they going to help us solve the closest vector problem, they're also going to help us solve the shortest vector problem. So this should be like huge alarm bells. Until I tell you they can only run fast or perform well. They can't do both. So as long as we're working in very high dimensional lattices, 2, these aren't really a concern. All right, before I tell you anything bad about lattices, we love them. We're going to indoctrinate you all into the Lattice Club. We love them, they're the best. We love them because generally in the community, they're accepted to be both classically and quantum secure, which is great. That's what we're going for. We love them because they're as hard on average as in the worst case. So if you think about a factoring problem, I can manufacture a really, really hard factoring problem. But like on average, if I give you a number, half the time it's divisible by 2. Right? So like the average case there is definitely not as hard as the worst case. What this lets us do is say, when we're trying to choose the public basis for our system, we can just pick any random one. We don't need to be worried about handcrafting a worst case scenario because they're just as hard on average as the worst case. We love them because they let us achieve what's called fully homomorphic encryption, which I will not talk about at all. If you're interested, talk to Kyle Yates. And they're generally understandable and easy to implement. So this means people trust them and they mess up the implementation less. They do have their problems though. And the main drawback is that in a naive implementation, it requires a very large public key. So for instance, FergoChem is one of the submissions that made it through the 3rd round of the NIST competition. It behind the scenes uses a matrix of size 640 by 640, and each integer has a bit length 16. If we do a little quick math, that's 6.5 million bits, which is like, okay, well, how much is normal? Standard algorithms right now use 24 things. So this is way bigger than what is reasonable. We can use special kinds of lattices to square root that key size, and that would put us back on par with standard algorithms. So we really want to do that, right? And this was first done in 2007-ish, when Michancio introduced ideal lattices to cryptography. These ones can be represented by a singular vector instead of a whole matrix. But we have no guarantee that they're as secure as general lattices. A little bit before that, Hofstein, Pfeiffer, and Silverman introduced a similar kind of lattice in their entry system. It also has no security guarantee. And we actually have some recent papers that seem to indicate that these ideal lattices are probably not as secure as general lattices. It's kind of more of a question of how much less secure. So in all of my work, I'm going to use a different kind of special lattice that's going to achieve the same size reduction, but I can have a security guarantee. How many people have had linear algebra? Okay, we're going to go through this very quickly. So if this is a vector, all of those numbers are integers. What I can do is I can split it up by just each individual entry, and a really nice vector that has all zeros and 1, 1. Because we can do this and it's so nice, we're going to call these standard bases of Zn. Yeah, it's Rn too, but I don't care about that. I just want to so we're going to do E1 to N, so that's where the 1 is in the vector location. If you didn't get any of that, it doesn't matter. Just know these are super special things, and I like them, and I'm going to use them. And I'm going to use them in this new subset of lattices. So I'm going to create a lattice by taking those nice vectors I just showed you and one extra vector that's rational. So that vector, I'm going to represent it as n different numerators and then one common denominator value. So n plus 1 numbers. I'm going to call this a simultaneous approximation lattice, and I'll tell you why in a bit. So also, this is a strict subset of lattices. Most lattices are not of this form. So most lattices are not of this form. So if we want to find a short vector in this situation, then we would need to find ai's and b that are all integers to get an integer combination of all of these vectors. But I kind of just split apart in A on the last slide. So let's put it back together into vector form. I could squish all those AIs, EIs into a vector A. So what I want is an integer vector A minus B times my original vector X. And I want that to be very short. Quick note, I'm gonna not let B be the least common denominator of X because that would be a little bit silly. Because then if I clear all the denominators in my fractions of X, then I'm going to be getting a true 0 vector. And remember, when we want to solve shortest vector problem, we care only about non-zero shortest vectors. Every lattice has a 0 vector, that's boring. So for each value of B that we pick, we can actually just figure out the A's by rounding each coordinate of B times X. So let's do that really quick. Let's look at this X vector. If I give you a particular B value of 301, then we're going to get this vector when we do the multiplication. And there's each one of those is pretty close to an integer. So if we take our A vector to just be each of those coordinates rounded, then when we do A minus BX, we find something that is very close to 0. So yeah, we found a short vector in the lattice generated by Z3 and X. And now your big question should be, how in the world did you find that B value? I just threw it out of nowhere. And that's actually kind of the point. This is a hard problem to do. It's hard to find that B value. This is what's called the simultaneous approximation problem, which is why they're called simultaneous approximation. So in the simultaneous approximation problem, we want to find an integer multiple, so a B, of a given vector X that is near an integer vector A. So solving the shortest vector problem in this particular kind of lattice is exactly the same as solving this problem. And in 2020, Dr. Daniel Martin, my advisor, showed that if we can solve this problem, then we can solve the shortest vector problem. And he used these SAP lattices in order to do that. So all of my work is kind of improving upon his. So this tells us that it is just as hard to solve the shortest vector problem in this special subset of lattices as it is in general. Which very importantly is not something you can say about ideal lattices, which is kind of the hot topic right now. So this is helpful. This is really important. And the benefit of this is that I only need n+1 numbers to tell you the whole lattice, right? I just need n numerators, one common denominator. So this is asymptotically just as hard, but I'm a little bit concerned about how big those n+1 numbers actually need to be in order for the security levels to remain the same as general. So that's exactly what I'm going to consider. And so in a general lattice, I'm going to have n squared numbers and some bit length bound on the entries. In Photochem, it was 16. In my new lattice, I'm going to have n+1 numbers times some bit length bound. So as long as I don't increase this by n times the general case, I still have a win here, right? So that's the goal. We want to see how much does that bit length need to grow. As long as it doesn't grow by n, we're good. In all the experiments, which I'll show you in a little bit, it actually seems to not even need to be close to n times. All right, so a little bit of theory, and then I'll move on. This is not what the main point of this is. But back in 2020, Daniel showed that we need to increase that most n to the 4th times the original. Not good enough, but it's a good starting point. Oh, I forgot to change this. This is actually proved now. We need to increase. I proved that in the worst case, we only need to increase by n squared times the original. Still not good enough, but a lot better. And that's all I've been able to do so far from the theoretical side. So once we were doing this, we're kind of not able to get this down to the n that we needed right now from the theory side. We kind of looked at a different question of, okay, what would happen if I just kept those bit length bounds the same? How much worse is the SAP lattice than general, right? It's kind of like, how bad is it? And so there's two main ways we can test this security. The first is just running one of those algorithms I told you about 10 slides ago, specifically the LLL algorithm. That's the one that turns bad bases into good bases. So how fast does it run? That's what we're going to do. So I'm going to generate a random lattice, time how fast this takes, generate an SAP lattice, time how fast it takes, and see what happens. We'll see how bad the SAP lattice is. Oh, it's not. It didn't fit. Okay. Well, across the bottom that you can't see is the dimension of the lattice. This is 50 and this is 300. This is roughly 150-ish. And yeah, I literally changed this 10 minutes before the talk, and I should have looked at it, but the y-axis is the average seconds it takes for LLL to run. The blue dots here are how long it takes for general lattices. So it's the important part that's cut off is that this is the curve for general lattices. This is the curve for the SAP lattices. So it's actually taking LLL significantly longer to run on this special subset than in general, which is good if we're looking for more security. It means that the attack is taking longer to terminate. Okay. But there's another way we can test security, and if we kind of win in one way and fail in the other, then it's we didn't really win. And the other way is to look at how well does this attack work, right? So if it takes longer to run, but it gives me a way better answer, you have to weigh your options. Is that really better? So how we're going to test this is by generating a random lattice. And we're going to use an algorithm to get the true shortest vector which we can only do in small dimensions because it's a really hard problem. And then we're going to use LLL to get the approximate shortest vector. So when we do that, we can just look at how well did it do. What we're going to take the length of the approximate shortest vector, see how short it is in terms of the length of the real. So the closer that this is to 1, the better the attack did, the worse security is. Okay, so we're going to do this for general. We'll do this for SAP. We'll see how much worse SAP is. That's what the other one was supposed to look like. Across the bottom is the dimension of the matrix. And across the y-axis is the approximate shortest vector length over the actual. So what we can see here is that for general lattices, the LLM algorithms runs decently well with this setup. But for these SAP lattices, it's significantly harder. It's performing worse, which means the security is bad. So this is actually huge. It looks like the LLL algorithm is taking longer to run and is performing significantly worse, which means that these are actually more secure than general lattices. So I told you I needed to not inflate by n, but this is not inflated at all. This is with the same bit. So I might even be able to make these keys smaller and keep the same security level. So this is super exciting, at least for me. And I'd love to know why this is true. Oh, also I can't go above 50 because the Palmetto cluster won't do it. It times out. We'll only have like 72 hours, and it runs for 72 hours and it does nothing. So that's like really bad and good in different ways. I'd love to know why this is true. Ask me again in like maybe 5 years. I really have no clue. And I'm probably not going to be able to get to that point before I graduate. But, okay, we have these really great things. And I told you nothing about the project that I said I would, that you can get involved in. We think these things are better than general. Got some theory and some experiments to show that. How do we actually use them in practice, right? I showed you a practical application of a general lattice to a crypto system. How do we use these lattices in a crypto system? And that's the question. It's not actually that straightforward because they do have this very unique structure, and that's where you come in. So this is exactly what I want your help with, right? So I'm looking for some undergraduate math and computer science majors, not necessarily a double. I'm looking for math majors and computer science majors to join in on this research project. And we're first gonna have to learn some stuff, right? I'm not expecting you to know anything about lattice-based cryptography, except maybe things that I said today, maybe not even that. So we'll learn about some history, about some number theory, lattices, cryptography, all the things we need to know. We'll spend some time doing that. Then we'll spend some time understanding how one particular system is actually implemented. Maybe multiple, but probably we'll just pick one. I have some ideas of which ones, but haven't determined that quite yet. Then we're going to try to do it. We're going to research some ways to take this crypto system and adapt it to using this new kind of lattice instead of general. Assuming we can do that, we're going to test everything thoroughly and hopefully write a paper, some sort of report about what we did, what we tried, what worked, what didn't work, and how these SAP lattices could actually be used in practice. The only prerequisites for joining the project is that you've had some linear algebra background. It's going to be a lot of linear algebra, so we do need to have that, or if you've had something, I don't know, you need to know linear algebra one way or another, whether you learned it here or not here. Unfortunately, we're not going to be taking any seniors right now because we started in the spring and we don't want to like be immediate because that's sad. So probably sophomore or junior year. If you're a freshman, you're super interested, you have some background, talk to me, might be able to work things out. Reasons why you should join. It's awesome. And I'm awesome and cool. And Daniel is really awesome and cool, and you should join us. But more realistically, it's actually really important, right? So this is a very active community of cryptography in this post-quantum era. There's a lot of work being done, and as far as I know, we're the only ones working on this kind of lattice. This kind of lattice seems to be significantly better. So this is actually really important work and has the potential to have a serious impact on the community, of course, depending on what the results show. It's also a really unique opportunity to participate in not only just an undergraduate research project, but an interdisciplinary project. So we're very expressly trying to work with math and computer science. We're definitely going to have some coding aspects to it, which is why I'm going to get some computer scientists in here as well. And it'll be really awesome. So that's all I have for you. If you're interested, obviously talk to me now, or that's my email. Shoot me an email, work something out. And I will leave you with this picture of an otter, because otters are also awesome.
Questions?
What was the randomized reduction? Shoot. You said randomized reduction
Yeah.
assumption or something?
Randomized reduction hypothesis.
Hypothesis, okay.
It's a thing that I always forget the precise wording, and so if there's like, I don't think there's any CS professors here who will like get mad at me, but I think basically it means that with probability 1, a random algorithm will.
Randomized reduction lemma. I'm a CS major.
Okay, sure.
Sorry, but I just did say it.
Yeah, but like it's like with probability 1, this thing will.
If you have like a 1/p probability of some algorithm terminating 1/p times, it's all log event, right? So, right?
It's exponential.
Well, you can, fair.
I don't know.
No, that's.
To be honest, I remembered at some point, and then no one's asked me that question in like a year, and I forgot. We can look it up. Or Daniel knows, because he doesn't forget things that much.
Yes, that's the age.
Yes.
And you know the name, Lil Paris, does that have anything to do with the ideas for algebra? With like ideals for.
Oh, yeah. So I don't have time to talk about it, but yes, ideal lattices directly correspond to ideals in the ring of it directly corresponds to the ring of integers and the ideals in that. I just don't work with them, so I didn't have time.
Other questions? So I have a question. So people that are interested in this should just contact you via email. And how long do they have? When are you looking to kind of get this, your team set up, so to speak?
We're looking to start, we would at most have 1 or 2 meetings this semester. We're gonna start real like actual research in this. But I'd like to know as soon as possible, because there's some funding questions in the background being figured out. But you don't have to commit until like, you have to sign up for a course or something, so maybe like, I don't know, November-ish, mid-November, yeah.
Yeah, that was what I was gonna ask about, what, if you're interested in this, is there going to be like some type of assessment and determine like, hey, are you competent enough to join, or like, what should we study, like to prepare for?
Have you had them in your undergrad?
Yes.
That's it.
Okay.
You passed, that was the assessment. Yeah, very little knowledge is required other than general curiosity and mathematical knowledge and linear algebra. So we will do a lot of linear. Other than that, we'll learn everything else on the job.
Other questions?
How many hours a week would you estimate this? What's time?
I think time commitments, you're probably committing to about 3 hours a week on average. If you're gonna do some sort of credit for it, because like That's how that works. You can always put more. If you're not taking it for credit of any sort, probably 1 or 2 hours, but we're looking for people who are like really want to actually work on this. So probably I would say about 3 hours. You will not be expected to work more than that unless you want to.
Other questions? Okay, don't forget, there's still pizza there, take it home, get the hero of your dorm. Other than that, we will see you all next week.
I think overall. Yeah. I hope students get something. Yeah, so we're gonna finish your theory, we're finishing up your theory in the next maybe few months or so. But that's the goal, I don't know if they'll like.
Oh, that's cool.
And we're, so, yeah, the ideal lattice, the recent thing, and it's really. Oh, yeah, so essentially, like when you have like a, right?